All right, for Calc 3, and this is for worksheet 14.7, the last one here that we'll be covering. Now what I'm going to do is kind of go back and look at Calc 1 in single variables. So you can kind of have something to compare to. So first off, looking into finding local max, local mins, and terrace points in single variables. Okay, so let's use something real simple. Let's say f of x equals x squared minus 4x. Now, in Algebra 2, you didn't have calculus, so one way we did this was, one, recognize that this is a parabola as a parent graph. And if we want to graph this out, we knew that we could cancel that out, set it equals 0. Factor out an x minus 4 equals 0. You get x equals 0 and x equals 4. And therefore a parabola would look something like this. And due to symmetry, that our local min would happen at x equals 2. Now later on, we were able to find this with the derivative, so f prime of x is 2x minus 4. Again, set it equals 0, you get x equals 2, and you can see that that is a local min. Now another way we could do this too is do, for local min, take a second derivative, f double prime of x, and we get 2, so therefore it's greater than 0. So therefore it was concave up. So therefore we would have a local min, knowing it by concavity. Okay. So, and that is, like I said, local min of a line, because that's what we're finding is tangent lines. Now, what we're going to be doing is this. We're going to be doing optimization in several variables. So what we're going to be finding is local mins, local max, but the other one is actually saddle points. And that's one reason why we were trying to draw those out for quite a bit, is so you know what a saddle point looks like. Now, these are dealing with planes, though. Okay, not a line. So tangent planes is our max and mins. So the steps that we're going to be looking at is, one, just like the other one, we're going to have to find critical values. Okay, 2, we're going to be finding what we call a discriminant. Okay, and I'm going to use D to represent the discriminant. Now, there's some proofs of this, but I'm just going to give it to you, and you just got to trust that it works. So the discriminant is this. It's the f second derivative, and we're talking partials here, of AB, and then times it by the second partial derivative of y, AB, minus f partial derivative of x, and then y squared of AB. Now remember, this can also be yx. Order does not matter. Now the third thing here is we're going to also be finding f of xx for something here. Okay. All right, so let's go through the rules. So once you have all that information, these are the rules that we'll have to follow. 1. If the discriminant is greater than 0, and there's two scenarios here, okay, and f of xx is greater than 0, okay, then what you have is a local min. Okay, and I kind of think of it as this would be like concave up, and we're talking planes here. That means my plane would be sitting on the bottom, so therefore that would create a local min. Now, if my discriminant is positive, but then my second derivative is less than 0, then you have a local max. And basically I think of again like this. Here's my concave down. So how is my plane going to sit? Would be sitting on top for a local max. Okay. All right. So, and then what happens if it's less than 0, the discriminant? Okay, well then what you have is a saddle point. It doesn't matter on the second derivative, you have just a saddle point. So what's left in my option? Well, the discriminant is equal to 0, and basically the test fails, which pretty much I consider that there is no such thing as local max and min for saddle points. Okay. Now the hard part of this is going to find the critical values. Okay, so let's go through two examples, and we'll call it quits. So here's the first example. So here's my function f of x comma y. And you have x cubed plus y cubed minus 12xy. Okay, so finding critical values first. So what I got to do here is do the first derivative of x. So this would be 3x squared minus 12y. And then f, first derivative of y, partial, 3y squared minus 12x. And then set equal to 0. And let's try to solve for, for one of the variables. So in this case, this would be, like, say, 12y equals 3x squared. 12 would be 3 over 12 x squared, or 1/4 x squared. Now, coming over on the other one, I would have 12x equals 3y squared, and 4x equals y squared. So in terms of substituting in, I'm going to take this piece here and plug it in there and solve for x. All right, now you can do different combinations here, but that's just the one I see right off the bat. So I have 4x equals 1/4 x squared squared, which gives me 1/16 x to the 4th. And multiply by 16 here, so I have 64x equals x to the 4th. Set it equal to 0. X to the 4th minus 64x equals 0. Take out an x. And what I have here is x equals 0 and x equals 4. Now if I come back up here and get my y value, y would be 0 there, so 1 point would be 0, 0. And here, if I plug in 4, y equals 1/4 4 squared would be y equals 4, so my other point is 4, 4. Like I said, that's the hard part. Okay, so there's our 2 points. So now we need to get our discriminant. Okay, so let me try to squeeze in. We've already done the first derivative, and this was for xy, and we had 3x squared minus 12y. And then my first derivative of y was 3y squared minus 12x. All right, let me move everything up. Okay, so now we need to do f of x, second derivative of x. That would give me 6x. F y would be 6y. And then I also need the derivative of f of x, y, or yx. It doesn't matter. So, coming back here, if I do the derivative of x, I get negative 12. And if I come over here and do the derivative of y, I get negative 12. So I get the same thing. All right, so what's my discriminant? Well, it'd be 6x, 6y, minus negative 12 squared. So I have 36xy minus 144. So now let's plug in my points, which was 0, 0, and 4, 4. All right, so let's do 0, 0 first. So I'll plug in 0, 0, I get negative 144. Well, that is less than 0. Okay, so anytime the discriminant is less than 0, it's a saddle point. Okay, now let's plug in 4, 4. Now I have 36 times 4 times 4 minus 144. I do believe that's going to be greater than 0. Okay. All right, so the question is it a local max or min? So I use my second derivative, f of xx of 4, 4. Now my value of this would be 6 times 4, which is going to be greater than 0. Okay, so think of this as concave up, my hillside. So how would my plane sit? My plane would sit on the bottom here, so that would be a local min. Okay. All right, and like I said, that's a local min of a plane. Okay. All right, let's go through one more example so you can kind of see how it works. Okay. So last example here, f of xy. Say x cubed minus xy plus y cubed. Okay, so to find my critical values, take the first derivative, partial derivative, of x and y. So partial derivative of x would be 3x squared minus y. Partial derivative of y would be negative x plus 3y squared. Set each equal to 0. So you have y equals 3x squared. Here you have x equals 3y squared. And it looks like I'm going to take this and play it into there. Now I could go either way, but I'm just going to go that way. So x equals 3, and I have 3x squared squared. So that would be 3 times 9x to the 4th, 27x to the 4th. And now I'll set it equal to 0 so I can try to find some factoring technique. And if it ever gets something ugly, remember you always have your graphing calculator to plug into your y1 to find your critical values. In this case, all I have to do is take out an x, and that would give me x equals 0, and this would be x cubed equals 127, which would be x equals 1/3. All right, now let's come back over here on my other equation here. So you got x equals 0 and x equals 1/3. So plug in there this value. I have 0, 0 for 1 point. and plugging in here, I'd have y equals 3 times 1/3 squared. So it looks like it'd be 1/3. So my other point would be 1/3 and 1/3. All right, like I said, that's the hard part. So now let's go ahead and do the discriminant. All right, let me rewrite my derivatives. So I've already done it once. So derivative of x is 3x squared minus y. Partial derivative of y, negative x plus 3y squared. Okay, so now I move it up. So do a second derivative. This would be 6x. Second derivative of y would be 6y. And I do need f of xy or yx. And I would always suggest to check it, do it both ways. So if I do the derivative of this one here, it'd be -1, and derivative of this one here, -1. Okay. All right. So my discriminant would be 6x times 6y minus -1 squared, and that would be 36xy minus 1. The points I want to check is 0, 0, and 1/3 and 1/3. Okay, so let's do 0, 0 first. -1, well, that's less than 0. So anytime the discriminant is less than 0, that is a saddle point. Okay, now let's do 1/3, 1/3. So 36, I have 1/3, 1/3 minus 1. So that's 9, 4 minus 1, so I have 3 less than 0, excuse me, greater than 0. So we have to come back to my second derivative. F of xx of xy, which is 6x. Now, if I plug in 1/3, 1/3, I get 2, which is greater than 0. So again, like I said, think of this as concave up in 3-dimensional. So it's concave up. And therefore my plane would be sitting on the bottom. So that would be a local min would be my plane. All right, so that is it.